Bonjour à tous. Nous avons aujourd'hui le plaisir de accueillir Bruno Buonomo de l'Italie, l'Université de Naples, qui va nous parler de Information Dependent Behavioral Models for Coronavirus Disease Transmission. So, Bruno, thank you for being with us today. So, we leave you for 30-45 minutes for your talk, please.
Okay, so thank you very much, Gabriel, for this very kind invitation. And so I hope to be a nice guest in your very, nice community concerning these COVID-19 problems. So as you said, I will talk about the information-dependent behavioral models for coronavirus disease transmission. This is the title of the talk. And so the outlines of the talk, I will present the talk in three very brief parts. The first part, I will present some basic material concerning the information-dependent epidemic models. And so generally speaking, about behavioral epidemiology. And I will show also one possible tool for working with this in this context, the so-called information index. So in the second part, I will mention first attempt to use a very simple model, which is called SIRI model. And this is an example of three-ways model in a way that I will explain in a few moments. And so we will get some first insights on coronavirus from very basic model. And so I will explain the role of the information coverage and information delay on the disease transmission. And in the last part, I will try a sort of comparison between the SARS epidemics in 2002 and 2003 and the SARS, 2.0 epidemics that we are experiencing now, the so-called COVID. And so when necessary, I will define the first epidemics just SARS and the second one COVID, like like is done usually in mass media. And so I will try a comparison based on mathematical modeling. Especially, I will talk about deterministic compartmental models. And finally, I will show some early plots concerning the case of COVID-19 in Italy. So let us start from the first part, the information-dependent epidemic models. So the role of information on the behavioral of people and the feedback that this may have on the transmission of the disease. So the very starting point is the basic SRR model. I think all of us are familiar with this kind of modeling. So the idea is that the whole population is divided into three compartments, so three disjoint groups. The susceptibles, the infectious, which in this model corresponds also to infectives. So we have infectives and infectious in this compartment, and the recovered one. So we have the recovery from I to R, which may be represented as a linear process, is this term here. And this process is the contagion, the transmission process, which is nonlinear in its nature because it involves two state variables, the susceptibles, the healthy peoples, and infectious. Now, a way of modeling the transmission is to consider a nonlinear term like this, where it appears explicitly the so-called force of infection. I mean the per capita rate at which susceptibles contracted the infection. So it's this function here. Now, we know that when this function is represented as a linear function of the number of infectious, which is also called the prevalence, then we have a new parameter, beta, which is a constant, a positive constant, and it's the so-called transmission rate. So when we do this, so that the transmission is bilinear, it means that we are assuming that the mass action law holds, so that the individuals are represented as interacting particles, and from a random encounter between susceptible and infectious, the infection may be transmitted with a certain probability. This means that in this transmission rate, we can consider this one as the product of two constants term, at least in this very simple description. One is the contact rate, and another one is the probability that from the contact, the contagion will take place. However, in the 70s, Vincenzo Capasso pointed out that this kind of description is not always realistic. He studied the case of cholera in southern Italy in 1973, and he stressed that sometimes it is realistic to consider a force of infection which is nonlinear. And in particular, it may be a saturating function, like in this case, and in this case as well. And so that this kind of functions are also called Halling type functions, or maybe also a non-monotone function like this one. And so that this kind of phenomena was also called in the literature some psychological or inhibitory effect, when a large number of infectious may produce a change in behavior of population, and so that this kind of functions will summarize this effect. So such early works, we can say now that I mean nowadays developed in a special branch of the mathematical epidemiology, which is called the behavioral epidemiology, and or more technically, the behavioral change models for infectious disease transmission. And here, the basic idea is that the human element is a key factor in the spread of infectious diseases, and so that this effect should be taken into account in order to understand how an epidemic will unfold. And there is an increasing number of papers concerning the behavioral change models. And for the people interested in this topic, I suggest the first collective book edited by Piero Manfredi and Alberto Donofrio in 2013, and also the larger review on statistical physics of vaccination. So this one is especially devoted to vaccination, that has been published in Physics Reports in 2016. An interesting case study in this context is the so-called pseudo-rational exemption to vaccination, which is, the choice to vaccinate or not vaccinate children made by parents on the basis of a balance between the perceived risk of the infection and to get damage from the infection, and the perceived risk of side effect from the vaccination. And so, in this case, it may happen that the vaccination coverage may decline as a result of fears about vaccination. So a very popular case was that one of MMR vaccine in the UK. After, the very well-known papers by Andrew Wakefield that connected this kind of vaccine to autism, so that the vaccination coverage declined pretty much, and 10 years more or less needed to recover the previous level of vaccination coverage. Of course, this kind of rational opposition, it's really pseudo-rational because it's quite myopic, because it takes place especially in regime of low prevalence and high vaccination coverage, where this low prevalence usually is just due to the large level of vaccination. So one can compare, for example, the reported measles case in UK before and after the introduction of measles vaccine in 1968. And of course, this is a quite important phenomena because a decline in vaccination coverage may produce a resurgence of the infection. So when we are trying to modeling this phenomena in the vaccination case, we can try to work with a modified version of the SIR model. So in this case, we have a new compartment, which is the compartment of vaccinated people. And as you can see now, compared with the SIR model that I have shown just before, now we have the demography. So we have a mortality and we have an input term. And a fraction of people at birth is immunized, so that we have the effect of vaccination in this term, and this is the vaccination coverage of newborns. As you can see here, there is this symbol M, and M is the information index. So of course, there are many possible ways to represent the behavioral effect of people, and the information index is just one of them. So the idea here is that the information takes time to reach the public due to time-consuming procedures such as clinical tests, notification of cases, and so on. And the public keeps memory of the past value of the state variables. Therefore, in the information index, there are three main ingredients. One is a delay. Another one is the memory kernel that should describe how the people keeps memory. And the third ingredient is the so-called message function, G. This function, as we will see in a while, represent the information, the message that is relevant to the public in determining its behavior. So therefore, the mathematical description of these three ingredients is just an integral term where we have the delay kernel here, and this is the message function. Now we can discuss about what is really relevant to the people in order to take a decision. For example, it could be the prevalence, or it could be the incidence, so the daily new cases of the disease. For a model like this, the new cases are represented by this term, the transmission term. And therefore, this means that in principle, this function depends on the two state variables, S and I in some way. And the link between the information index and the model is represented by this function here. As you can see, here there is a constant term, P0, which mimics the idea that there is a fraction of people that is immunized regardless of the information or rumors concerning the disease. And another fraction depends just on the information. So this function P, we will discuss this function P in the next slide, and we will start to describe the way that the delay kernel may be represented. Of course, the choice is not unique, but the Erlang distribution works pretty much for this kind of problems, because it may represent, the case of the memory gives a greater weight on the current time here, and then is exponentially decreasing, which means an Erlang distribution of order 1, or maybe more focused on past events. So when the order is greater than 1. Using an Erlang distribution is very useful from a point of view, a mathematical point of view, because one can reduce the system to an ordinary differential equation systems by using the linear chain trick. And we have also a very interesting physical meaning of this parameter A, which is, the inverse of the average delay of the information. As far as the function P is concerned, one possible way to represent this is to consider a saturating functions of Holling type. So for example, the Holling type 2 function is just a function like this. Which kind of important results may come from using this kind of modeling approach? So let us consider this plot, which is also called the bifurcation diagram. So this plot refers to the modified model that we have just seen, when the vaccination, the pediatric vaccination is considered. And we consider a Holling type 2 function P. And as you can see here, the message function is a linear function of the prevalence. So this means that the social alarm is produced by the presence of infectious in the community, and the number of these people, the number of these people is modulated by this constant K, which represents the information coverage. And the delay kernel is assumed to be just an exponential delay kernel, so first order Erlang distribution. So here on the horizontal axis, we have the information coverage. So this is an area of low coverage. This is an area of high coverage. And on the vertical axis, we have the information delay. So in this area, we have low delay, because A is just the, the inverse of the information delay. And as you can see, if the information coverage is very low, then we are in a region where the system is at an locally asymptotically stable endemic state. So it is in a stable state. As you can see here, there is a branch of values of A, and in this area, the system is experiencing sustained oscillations. So if we are, inside the letter O, this word, so the system is experiencing an unstable state, and one won't, the public health system won't try to stabilize the system. It could be an idea to enlarge the delay, but this means that I will move downwards, whereas the right way to get a larger region of stabilization here is just to move upwards. So this is the kind of results that one can get by modulating the two information parameter K and A. Of course, now we are talking about vaccination, but it is not only vaccination, because we have many cases of symptoms of a behavioral change in contacts in response to epidemic outbreak. We are experiencing this now for COVID-19, but there are a lot of past examples, like I mean the SARS, of course, but also the swine flu, and again, I mean other examples may be the HIV. In all these cases, one have a decline in contacts between individuals. And just to make an example, if we try to consider a modified version of the SRR model in which the information has an influence on the contact rate, it has been proved that the social behavior change alone may trigger sustained oscillations in this case, but when the memory is at least a second order Erlang distribution. Okay, so now we can have a look at a very basic, simple model to have first insights about how this kind of approach may be used in case of coronavirus disease. I mean, I tried to get some results by using this very simple model at the beginning of February. This is very important to point out, because at that time we had the epidemics in China, but no cases in Europe at that time. So the scenario that one can consider is one of a community where a relatively small quantity of infectious is present at the time of a public health system campaign to favor protective actions just on a voluntary basis. Because here the idea is to stress the role of information. So we have no mandatory actions. And the choice to get protected or not is assumed to depend, as in the vaccination case that we have seen before, in part on the available information and the rumors concerning the spread of the disease in the community. So, of course, the vaccination is exactly the form of protective actions that works quite well in this kind of description. And we hope to have vaccination very soon for COVID. But generally speaking, this may be applied also to quarantine. So why the choice of this model, the SRRI model, which is another version of the SR classical model? Because here we have a three-way dynamics, depending on the value of the basic reproduction number. So if the basic reproduction number is less than 1, as usually, I mean, most of the cases, but not all the cases happens, we have that no epidemic will occur. So starting from a certain number of infectious in the community, we will just see a decline of this number. If the basic reproduction number assumes a value in this interval, then we will observe a single epidemic outbreak. So the infectious will increase, will reach a maximum, and then the disease will be eliminated by the community. If the basic reproduction number is greater than this threshold value here, then, then the epidemic outbreak will follow, and the disease will permanently remain within the population because we will reach an endemic state. And these three, these three possibilities were three of the possibilities that we were talking about at the beginning of the February concerning the COVID. Now, I want to stress that for the classical SIR model, it's not possible to have an endemic state. In order to have an endemic state, you should have a replacement of susceptible individuals. And therefore, you can have the endemic state for the SIR model if you add the demography. I mean, some people entering into the system with immigration or birth, and people also going out of the system because of immigration of maybe death. However, here the replacement is due to the reinfection. So reinfection is a phenomenon which has been observed in past coronavirus. And for example, for SARS, it was estimated to be 3 years. We know that the epidemic of SARS, the duration was lasted 10 months, more or less. So we had no effect of reinfection, but nobody knows about COVID. So the information-dependent version of SIRI model is, this system of differential equations, where we also are considering, in this case, that the protective action is not fully protective. So, for example, vaccinated people may be infected with the reduced rate of infection, but may be infected in any case. Then we can set again the coupling with the Holding type 2 function. Again, in the simplest case, we can consider a prevalence dependent message, and also an first order Erlang distribution, as we have done before. Again, I will remember that the parameter K is the information coverage, and the parameter A takes the meaning of the inverse of the average time delay. And if we try to set the epidemiological parameter values, so to have a parametrization based on early estimation of novel coronavirus, this kind of estimations were the only estimations available, more or less, at that time. So, for example, here we can refer to the city of Wuhan, and it was estimated to have a transmission rate of 1.07 and the infectious period 3.6 days. One of the best aspects of this very simple model is that you don't need to estimate too much parameter in this case. And the basic reproduction number is 3.85, which is agreement with the estimates. Of course, if we try to evaluate the basic reproduction number for this system, we will get exactly the same result. And the threshold value for the reinfection in this case is 0.2. So we can consider a baseline value for the information parameters that represents a very bad information, very bad, so that we have 0.2 as the information coverage and a very large delay. This is up to 4 months. However, if we try just to do this kind of simulation, so when the infection is in some way negligible here, so it's very low, we have a sort of epidemic curve, which we can compare with the Chinese case, so that we use these numbers. And of course, we can compare with the yellow one. And of course, it's very different with a very, the peak is reached quite quickly, and with a very high number of cases compared with this. But this is due to the fact that we have just considered a very simple model without any mandatory actions, which really happened in the real world, I mean. But however, we can see that the duration of epidemics is approximately the same. I mean, around 2 months, which is in agreement with this case. Of course, when you have this kind of model, you can try to get other informations, other results from these information parameters. And so here you can see the cumulative incidence compared to the information coverage. And this is the variation compared to the baseline case that we have seen before. Here we have very low level of reinfection. So we are below the threshold. This is 0.2. And here we have above. So this is 0.4. And I mean, we can see here that a reduction till 80% may be reached by increasing the value of the information coverage till, I mean, 0.99. Of course, this kind of plot may be also read from right to left, and to see which kind of, of problems, which kind of issues arise when the information coverage is very low. In this case, we can also see this is the catastrophic case, because we have the reinsurgence of the disease because of this very high level of reinfection. But however, we can have this problem is quickly recovered because there is a threshold value between 0.2 and 0.3 of the information coverage, such that the system may pass from the endemic to non-endemic asymptotic state. So this may be quickly recovered. Consider that here we are starting from 0.2. The same kind of results may be obtained by considering the effect of social alarm, represented in this case by the information delay. And again, we can see that starting from, this very huge delay, we can have a reduction till 75% by reducing this value to very few days. So having this kind of results in mind, the idea is how to compare these two cases, SARS and COVID, and how to implement what we know from SARS, which is a kind of exercise that in many fields has been done. Try to use what was known for SARS and try to implement for COVID. So in this case, I would like to present this model, which has been published in 2004 by a large group of researchers concerning the modeling strategies for SARS. And I call this one an after epidemic model, because it has been published in 2004. So after that, the outbreak ended. The SARS tried to return back in 2004, but it does not succeed in that. So this means that everything was known about the evolution of the epidemic at that time. So what we can see here is again a compartmental model where we have susceptible. This compartment usually is associated to the exposed individuals. The exposed ones are the people that are infected but not yet infectious. But in this case, the meaning is different. These people here are asymptomatic people. And here we have the infectious, which correspond also to the symptomatic class. And we have the recovered. And here we have people in quarantine and isolated people. Now, of course, when we are comparing these two epidemics, we have a lot of differences. I mean, this list is not exhaustive, but first of all, I mean the dimension of the epidemics, because SARS just accounted of more or less 8,000 cases around the world and 800 deaths. So it's not comparable with the case of COVID. And at that time, a rapid diagnostic or screening test was not available, so that the diagnosis was made just by associating the presence of clinical symptoms in conjunction with exposure to a known source of SARS. And this is more or less what has been done in the first stage of COVID epidemics, at least in Italy as well. And then another very big difference is that the SARS was believed to be transmitted exclusively by symptomatic individuals, and the symptoms were very, usually were very severe symptoms. So did not result in infection with mild symptoms usually, and for this reason, was easier to identify the transmission chains and block them with the isolation of the patients, and it was also easier to have a mathematical modeling, because it was possible to organize the compartments as I have just shown. So by considering the asymptomatic and the symptomatic like infectious only. However, if we consider this model, the force of infection maybe, it involves in several ways several classes here. And especially you can see that it is possible for people in quarantine still to infect individuals, and also people, isolated people, because of the problem that they had at that time. The problem was that the hospitals was unable to perfectly isolate the patients, at least in the first phase of the epidemics. So it was necessary to implement the measures aimed at following a strict adherence to the health protocols. And this day here, 20 of April in 2003, was identified as the day in which this kind of protection was obtained. So this means that these arrows that you can see from these compartments to these compartments here are, does not appear in any time when you are running this model. However, if you sorry, I just heard some noise. I don't know if,
No,
are you hearing me? Okay.
Don't worry.
So if you compare the results of this model with the real data, we can see that there is a very good fit. Here you can see the cumulative death in Hong Kong, and this is the same for the Great Toronto area. These ones are only samples, but there are many on the paper. You can see, and here you have the cumulative death in Singapore, and here you have the probable cases, and the probable cases. The cases of SARS were defined just probable at that time, as we have seen before. Clearly, here you have two protective actions. One is quarantine, another one is isolations. And these two plots are interesting because you can see here a level plots of the basic reproduction number. This one is referred to the Great Toronto Area before the the perfect isolation was obtained, and this is after that. And as you can see here, on this axis you have the average delays until quarantine, and this is the average delays until isolations. And in the level plots you will not see the number 1. So it is not possible to reduce the basic reproduction number under the threshold which will ensure the elimination of the disease in this case. However, when the protective measures in the hospitals was obtained, here the scenario is quite different, because as you can see here, this is the line corresponding to R0 equal to 1, and so with by considering values of these two parameters, gamma 1 and gamma 2, in this region here, you can reach the target. Clearly, when we are talking about real cases concerning COVID, and I will refer especially to Italy, also here you have to consider government actions. More or less, we can divide the actions of the government in four moments here. The first day we had in March the 1st, we had the partial lockdown in a restricted area of northern Italy, and then this sort of partial lockdown was extended to the entire nations in March 9, and then we get the full lockdown with the closing off of all non-essential companies and manufacturing plants. And we are still in here, although starting from next Monday, we will begin the so-called phase 2 with a slight restriction easing, which involves mostly the companies and plants. Very recently, it has been published. It is available from the proceedings of National Academy of Science, starting from the April the 6th, a model which has been done by a group of researchers from several institutions, and in particular the Polytechnical University in Milan, where a kind of description made by compartment models, which is similar to the SARS model that we have seen before, has been built. So here, the results has been obtained by using a sort of meta-community model that includes a network of more than 100 nodes representative of Italian provinces and the metropolitan area. However, the core model is this one. So this means that this model works in any of these networks and then are connected. And in these models, a special emphasis is devoted to the class of pre-symptomatic individuals, which seems to play a major role in the transmission of the disease. Whereas, so that you have here susceptibles, exposed ones, so latent individuals, then you have post-latent or maybe pre-symptomatic individuals. Then you have this class, which is asymptomatic or mild symptomatics, so they are together. These ones are infectious, severely infected people that can die or maybe hospitalized, and this is quarantine and this is recovery. When you try to apply this model, you will get some estimates. One estimate is, you can see these numbers, so 200,000 hospitalization and 6 million infections averted due to the government action and the consequent changes in social behaviors and awareness. So what you have is an effect of the government action, which is considered as mandatory in some way. So a reduction of the contact rate, and this is the kind of information you can get. And we have also to say that this model estimates 600,000 total infectious individuals as of March 25, which was the end day of this analysis. But the actual official number was, quite less than this. So that, this kind of results may be used in several ways, also by saying that the official numbers are very low compared to what happens in, in the real scenario. Clearly, we can try to adapt a little bit this kind of approach by giving new definitions of the state variables according to new evidences regarding the virus and the epidemiological parameters. For example, we now know that there is or at least we have official reports that say that there is a negligible role of the truly asymptomatic individuals. The people that will not develop symptoms during his infections. And of course, if you try to have this approach, in these two blue arrows represent the points where the information may play a very central role. In social distance control and also in quarantine. As we can see, I every day, just by looking at the mass media, TV or other news, so it's very difficult to contain the people in a house. So I have just very few plots. That's very preliminary research that we are doing with my group, and in particular with the Rossella Della Marca, who is working in the University of Parma. And here you can see the real data. The blue line. So, and this is the black line is what we observe from the model where the information is not taken into account. So we have no information effect in this case. Here you have the cumulative incidence curve in Italy, and this is the cumulative death curve. So when you try to set the information, you can see that there is a perfect adherence for the cumulative death corresponding to an information coverage of 0.8 and an information delay of 3 days in the average. And you can see also the difference of the effect due to the cumulative incidence. Of course, when the incidence is very high, so you have a very high prevalence as well. And that's why the social alarm may push the people to respect the rules. And again, we can see the difference of the model without information on the quarantine, in this case, quarantined individuals. And again, we have the comparison with the effect of information, which push the people again to respect the rules, so that the quarantine level is higher and is closer to the real data. That's one are just preliminary, and I think that's enough. So that I want just to leave you with some references the two main papers that I've mentioned in the last parts, the two main reference for the behavioral epidemiology, and some personal contribution to very recent ones on the use of behavioral models, and in particular on the information index. And so thank you very much for the invitation. Thank you very much for your attention.
Okay. Thank you, Bruno, for this presentation. So we will now take some questions if there are some. So on va prendre quelques questions si jamais il y en a. Donc n'hésitez pas à poser la question ou à mettre sur votre intention de poser une question sur la conversation. Maybe I will start with a question. So for the Chinese case, there is the information was two types. So there was an official information from the official channels, and also a private information. Can you take into account this kind of difference? Because I guess there the private information was maybe even more important because the official information was somehow distorted.
But the point is that so you are saying that the official one should be, I mean, is underestimates. So
probably, or yeah.
Yeah, this is what it seems. So there are some early models that have used for Italy exactly the official data from China, and according to that values, the epidemic in Italy should have been quite mild compared to what happens in the reality. And so how can we say that that kind of models are wrong, or that we have been unlucky, or probably our control measure didn't work? Or we can also say, I mean, that probably that informations, that official numbers were very underestimates. Of course, when we consider this kind of very simple modeling, we are using a social alarm, which depends on the prevalence. But as you can see, this number is modulated by the information coverage K. Therefore, we don't know exactly the number I. This is just the number of infectious is just the results of the model. We don't know the official ones. What we know is the number of the people, the number of infectious that may produce a change in your behavior, so that you can modulate that parameter K to take into account of only the official version, the governmental version, which means that K will be quite a low number, or in any case will be less than the number that you can consider for private communications, because private communications probably more I mean, private communication will overestimate the number compared to the official one, and so you can modulate this effect by considering the information coverage parameter K.
Thank you. So any other question? So, let me see.
Yes, I have a question regarding the death. In France, we have the problem that there are the deaths in hospitals, there are the deaths at home, there are the deaths in retired home, in medical care for all people. And how do you take this into account? Because I'm not sure the official information takes all this into account.
Yeah, the point is that I think we will discover what happened probably after the infection. The problem that we have today with COVID is, especially in Italy, is related to the retirement homes, and partially regarding also the hospitals. Of course, this has been considered in the SARS model that I have shown before, in the sense that some of these connections between, for example, the class of infectious and the class of hospitalized people, and you know that the hospitalized people may still have a role in the force of infection, then you can modulate the parameters in the force of infection to take into account that the protection inside the retirement homes and inside the hospitals was not perfect. And you can take into account of this by modulating the parameters that appears in the force of infection. However, in this moment, you can just guess that once. You can just guess, and especially, I think a better fit would be by considering an age-structured model, because of course the retirement homes problem is especially related to the old age, and probably this kind of fitting will be done after the infection, when we will get more information, more data about this kind of phenomenon.
Okay, thank you. And if I may, I have a second question.
Sure.
Can you use this model for a deconfinement scenario? And if yes, what do you modulate then?
Can you please repeat?
Can you use this kind of model to help making a deconfinement scenario? You know, there are big discussions all over Europe to know how you need to deconfine to avoid second epidemic or other things. And if yes, how do you modulate this deconfinement scenario? What would you change in your parameters to?
Okay, so I want to stress a very important point. The idea is not to build a model to forecast the evolution of the epidemics. There are, of course, many researchers that are working on this. There are already a lot of papers available, so that some of them now we can check that are completely wrong. Some of them are more or less right. So we have a lot of contribution in this direction. The contribution I'm trying to work with is just the effect of the information during the lockdown containment. So the lockdown containments, the containment that has been restrictions that has been done by the governments that are now close to end. So the idea is how to communicate the number of cases, the new cases, the number of infectious, and I mean all the official data, how to communicate it and which kind of effects this may have on the people during containment actions like this. Clearly, it's a quite specific problem, because after that we can get information about this, so this kind of results, we can understand in the case that the disease we will have again the insurgence of this disease next year. Probably we can be we can have more information about the effect of lockdowns and how to manage it. Clearly, if you are thinking about different containment procedures and different kind of restrictions, then you should modulate the model by considering the right timing and trying to estimate the right parameters in that case. But of course, you should change a little bit the model, because what we are looking now is just to see the effect of a full closure of activities, working activities. The full lockdown also means that you cannot just go around. You have just you can just move for very essential reasons. So it's a quite specific kind of restrictions.
Okay, thank you very much.
Thank you, Bruno. So I see no other question at this moment, so the time is already up. So thank you again for your kind.
Thank you, Gabriel. I hope to see you soon.
Yeah,
I mean, but not in the web version.
Sure.
Yeah.
Sure.
Okay. So thank you to everybody, and see you soon.
Thank you. Bye bye.